Support vector machine. This is a supervised machine learning algorithm used for both classification and regression. It is a powerful machine learning algorithm used for linear or nonlinear classification, regression, and even outlier detection tasks. Why should someone choose support vector over k-nearest neighbor or logistic regression when you want to classify? Because remember, when we were classifying using logistic regression, naive-based classifier, or random forest, we were not taking into consideration the outliers. But support vector machine will take into the consideration the outliers. So at the end of the day, even the outlier will have their own class of outliers. So that's how powerful it is. Then another feature that makes it more powerful is that it can also be used for both linear and nonlinear classification. So the data set do not have to be to form a linear relationship. Even nonlinear, you can still form a relationship. Support vector machines can actually be used for both classification or regression problems, but most of the time you will find them used for classification. And I think I gave you a nota bene yesterday that when it is for regression, kindly go for models that work best for regression. Support vector machines it works as a discriminate classifier and can define a decision boundary, sometimes called an optimal hyperplane, that provides a function which separates the classes. So at the basis of support vector machine is what we call a hyperplane, a straight line that separates classes. So data scientists often try to find the best hyperplane, or rather the best line that separates the classes and ensures that the separation is actually done in a fair manner, free and fair election that you are used to in Kenya. It's always a fallacy. So when any new data points are then mapped onto the same space of the others, they will be categorized into the correct class. So applications of support vector machine. It supports a wide variety of tasks such as text classification, image classification, spam detection, handwriting identification, gene expression analysis, face detection, and anomaly detection. I want to focus on number 7 because that's the project we are going to handle, anomaly detection. So support vector machine can be used to support anomaly detection. And how does it support this? We said that outliers are data points that deviate greatly from others. I want you to look at these transactions in a bank. So the transactions in a bank are characterized by previous transaction history, or even the normal transactions that the bank expects. But sometimes there can be an overboard of transaction. An account can even start receiving 1 bob per day for like every second and receive 1 bob. Then the bank can be no, this is an outlier. You see? So that is what we call anomaly. Support vector machine is very powerful in detecting such like transactions, and is the one that is used in anomaly detection in the bank. Advantages: they are adaptable and efficient in a variety of applications because they can manage high dimensional data and nonlinear relationships. I think the best reason why people use support vector machine in any data is because even if you're not sure of the type of data of relationship that exists between data points, support vector machine can still be implemented in both linear and nonlinear data. And even if it has high dimension, by high dimension I mean it is a wide data. It has 100 columns, such like that one still do not prevent you from implementing a support vector machine. They are very effective as we try to find the maximum separating hyperplane between the different classes available in the target feature. Yeah, you want to classify items into different groups and you're going to see the process. So we are always trying, first of all, trial and error in drawing a set line that separates these classes and ensuring that we do a free and fair separation, so that a data point with a property do not find itself in a class with other properties. Everything that has an advantage must have a disadvantage. Not suitable for large data sets because it's high training time. it takes more time in training compared to naive-Bayes classifier. Aya, tumesema we always try to draw lines that separates the best classes. So it works poorly with overlapping classes, in that, what if we find, you remember the purple blue circles and stars? Some stars were inside circles and some circles were inside stars. Those are what we call overlapping classes. So you are to draw a set line separating the classes. Can you? So it works poorly with that. So it is also sensitive to the type of kernel used. Kernel, you are going to see what it is hapo mbele. Now, it is not the kernel you are used to. Okay, so when we have overlapping classes, there is a very, remember we say there are three types of machine learning: supervised, unsupervised, and reinforcement. So let us bring our focus to supervised. We've tried our level best to use support vector machine to implement in an overlapping classes, and it has really not, it was not tenable. So the best thing we do, we to give the machine instruction to try and understand the pattern on its own. So in that case, we use unsupervised learning technique. And that's where we are going to get into once we are done with supervised. So you are going to see how unsupervised can be used and when it should be used. Of course, it should be used when you want the data to identify, the algorithm to identify patterns in the data on its own. I wanted to get these terminologies into your RAM, brain RAM, hyperplane, support vectors, margin, kernel, kernel trick, hard margins, soft margin, C, Hange loss, and dual problem. All these are mathematical terms, and support vector machine is one of the machine learning algorithm. It was coined by, was it a Hong Kong professor, but in US? Is it a Chinese or Hong Kong? I don't know. But just from the Asian continent, but he was working in the US. So he's the one who coined all these. The first one is hyperplane. A hyperplane is the decision boundary that is used to separate the data points of different classes in a feature space. In the case of a linear classification, it will be a linear equation: wx plus b is equals to 0. This one, we are not going to look into the mathematics behind it, because thank God we have a support vector model that had been pre-built. So our task is just to train it on our data. Actually, the one who invented this is the one who built it. So hyperplane, think of this as a straight line that tends to separate classes of different data points. For example, in a class of ladies and gents, if you separate it using vile walikuwa wanafanya kitambo, using an empty space in the middle of the class, that empty space can be referred to as a hyperplane. The next one is the support vectors. Support vectors are the closest data points to the hyperplane, which makes a critical role in deciding the hyperplane and margin. Now, the first row of the locker near the line, so that is what we call support vectors. It is the row that identifies that hapa ndio wasichana wameanzia. Yes, kitu kama hiyo. So in mathematical term or in data term, it is the row that identifies that this is where the class of this data point starts. So that's why we are saying that they are the closest data points to the hyperplane, which makes a critical role in deciding the hyperplane and margin. Unaona? So the data points that are next to the hyperplane, that makes you see that, no, you know what? These are purple circles, purple stars, and these are blue circles. So draw a line here. Those are what we call support vectors. So they are the data points. In fact, they are data points. Then you have the margin. So the margin between the support vector and hyperplane, that is the distance between the middle of the row, the middle of the space that was left in a class and the first locker row. So that is the margin. So it's the distance between the support vector and hyperplane. The distance between the data point that was used to make a decision that this is a data point that belongs to this class, and the line that separates the two classes. And the main objective of the support vector machine algorithm is to maximize the margin. Umesikia hapo? So we are going to what I love about our role, you are always trying to answer a problem. And now in support vector machine, we are always trying to enlarge this margin to make it as big as possible so that the separation is actually realized at a very, very effective degree. In that, you can remember, you can imagine if the data points are so close to each other and the margin is too small, we are susceptible to getting a data point of a different class in this current class, and that's not something that we want to do. We always want that each and every data point during classification is always in its exact class. So the main objective of support vector machine algorithm is to maximize this margin. So the wider the margin, this one indicates that's a better classification performance. In simple terms, a margin is a gap between the two lines on the closest class points. And this is calculated as the perpendicular distance from the line to support vectors or closest points. So it must form 90 degrees from the support vector to the hyperplane. If the margin is larger in between the classes, then it is considered a good margin. A smaller margin is a bad margin. Kernel. Nice. This is the mathematical function which is used in support vector machine to map the original input data points into highly dimensional feature spaces so that the hyperplane can be easily found even if the data points are not clearly separable in the original input space. Some of the common kernel functions are linear, polynomial, radial basis function, and sigmoid. This is a hyperparameter in support vector, and you should know it. Most of the time, we are always going to use linear or polynomial. Kernel is a mathematical function that helps us identify which data point to be in which class. And this mathematical function is dependent on the data point. For example, if we have y response variable and the x independent variables, then probably this one will be a linear equation. So the kernel will be linear kernel. Now, but sometimes you might have an inverse. For example, y is equals to 1 over x plus 1 over x squared plus 1 over x cubed. Kitu kama hiyo. When such an equation is done, then that one will be a polynomial. Or polynomial in that because of the increasing power as you move along the line. So it is always going to help us know which one to use better. But as I said, this is a parameter, so it was pre-trained. Our task is just to implement kernel equals to linear. Then look at the accuracy. When accuracy is above 80 or below 80, you try using kernel is equals to polynomial. So when you find polynomial is 90, then it means that the data point fits well with polynomial and not linear. So you are going to see how we do it. But others like radial basis function, RBF, and sigmoid can also be used, but not relevant or not commonly used. So kernel trick, this is a technique where the kernel takes a low dimensional input space and transform it into a higher dimensional space. So kernel is a technique where the function takes I mean the fitting of data points. Uh, we talked of the margin being as a distance between one and the other. Now the fitting of the data points can be done in a high precision. When it is done in high precision, then that is what we call high dimensional space. So the kernel trick is the function or function optimizer that can be used to ensure that the classes contains what it should contain. In other words, you can say that it converts non-separable problem to separable problems. Kernel trick helps you to build a more accurate classifier. And in the later reading, you're going to learn how this technique works. Hard margin. Of course, you know what a margin is. So the hard margin is just a continuation of the margin. The maximum margin hyperplane or the hard margin hyperplane is a hyperplane that properly separates the data points of different categories without any misclassifications. So it is actually the distance that exists perfectly. But soft margin is the opposite. When the data is not perfectly separable or contains outliers, support vector machine permits a soft margin technique. Now, in as much as we can strive to have a hard margin, it is always recommended we use soft margin because many data points in the world, over 99.99% of data points in the world supports soft margin. You will always find an anomaly in the data point. That is in simpler words. So each data point has a slack variable introduced by the soft margin SVM formulation, which softens the strict margin requirement and permits certain misclassifications on violations. So it discovers a compromise between increasing the margin and reducing violations. Why should we use soft margin if it supports that? Because first of all, number one, the data sets, the real world data sets are not perfect. So when you implement hard margin, it basically means that you are trying to say a fallacy, like you are trying to implement what is false. So it is something that will never happen. So you will just implement hard margin by theory, but in real sense, soft margin iko kwa data. So the best thing to do is to implement soft margin, unless you are sure that you've cleaned the data well and you know what you are doing. See, these are parameters. A margin maximization and misclassification finds are balanced by the regularization. That one, parameter C in support vector machine. We had a biology teacher. So we will struggle with pronouncing. There's this word homostasis in biology, homo something. I don't think if you can remember it. So most of the time when we reach there, you will you will start you will just start dictating notes. Then when you reach there and asema that one. So again andike kwa chalkboard, then akifika hapo that one. So I think I'm also going to do that here. But this is basically a margin maximization and misclassification finds. It is basically a parameter that tends to maximize margins. So remember we said in this that our main focus or our main target is always to ensure that we have a very big margin to maximize the margin. The parameter or the function that can help us do that is the C. Okay, when you look at the formula for this thing, it's a very long formula which will take you years to understand. So hata mimi sijuangi vizuri, but I have it in my notes. So the penalty for going over the margin or misclassifying data items is decided by rate. So a stricter penalty is imposed with a greater value of C, which results in a smaller margin and perhaps fewer misclassifications. So you should always try to put a moderate. Remember, this C is the regularizer. And in machine learning, what did we say? You can try to be as strict as you may want, but something is waiting you up mbele. What is it? What is it? Overfitting or underfitting. So you must ensure you use maybe a grid search to ensure that you get the correct value of C that might end up giving you the best result. Otherwise, you are always prone to overfitting. It's just waiting for you, waiting to pounce on you. That is. Then we have this logical loss called Hange loss. So this is a typical loss function in support vector machines, which punishes incorrect classifications or margin violations. The objective function in support vector machine is frequently formed by combining it with the regularization term. What's this word? Regularization. Okay. Now, uh, sometimes we might tend to try as much as we can to classify items into different classes. Then we can try as much as we can to regulate it using C. But at the end of the day, we are not perfect. We can find 90%. So this 10% is what we can refer to as a Hange loss. It is the typical loss function in support vector machine. The dual problem, the dual problem of the optimization problem that requires locating the Lagrange multipliers related to the support vectors can be used to solve support vector machine. So the dual formulation enables the use of kernel tricks and more effective computing. It uses what is called the Lagrange multipliers. This one was my nightmare by the way, I don't want to lie, I got soup in this. Eh, na ilinisumbua hata hiyo ingine tena nikafanya soup tena nika fail. It was my nightmare. I didn't like it. This is it. The formula here. F of x or y is the response variable. Then the x is the independent variable or the independent variables. So first of all, I want you to note this. F of x is the response variable y. So y, we can have y naught, y1, y2, all the way up to yn, the observations. Then when you to implement Lagrange multiplier polynomial, that's why I said it may be linear or polynomial. So this is the polynomial one. You take x minus x1 all over x naught minus x1, where x naught is basically a certain predetermined value of x. So it is where the basis of decision making starts. I don't know how to explain it, but this thing, again, as you can see, we have second degree multiplier. You can even go to n Lagrange n order Lagrange n order interpolation formula. So that one means that we are going to have so many multiplication of the differences of x's. So as you can see, we have x1. Let me use the Lagrange first order interpolation formula. I never knew I will one day teach these things. Yeah. But the value of x minus x1, x1 basically is the first position of x, all over x naught minus x1 times y naught. Y naught is the first position of y. That is to say, let me bring up a paint. So we have y, the response variable, maybe the midterm exams. Then we have cut 1. Then we have cut 2. So maybe cut 1 and cut 2 is used to regress y. Okay, now we are using support vector regressor, not classifier. Cut 1 and cut 2 may be used to regress y. So this one is what we call y naught, y1, y2, y3. Similarly, this is what we call x naught, x1, x2, x3. Then so let us call it x1 naught, x11, x12, x31. Then this one is x2 naught, x21, x22, x3, x23. Then there is a value of x. In most cases, this x is always calculated by just summing xi's, then divide by n. So in short, finding the mean. So Lagrange formula always say f of x is equals to x minus x1 all over x naught minus x1 y naught plus hivyo hivyo mpaka umalize. So y, that is say now y is equals to let's say it was 5, then my x1 was 3 all over x naught we should be now 3, something like 4 minus x1 with 3. Then why not, let's say if it was 2, then you multiply until you're done. This is first order if it's just 1. Then second order if you move to 2, the third order evo. And at the end of the day, you can even move up to an nth order. So that's how, okay, this mathematical thing was developed for a support vector machine, and it's the one that is used to implement polynomial a kernel, the kernel we talked about. So think of the kernel as the type of model that exists between response variables and the independent variables, because it is. Kernel tries to identify the kind of relationship that exists between the y variable and the x variable. So the dual problem, it is a problem that requires locating the Lagrange multipliers related to the support vectors that can be used to solve SVM. So this formula is what we call the Lagrange multipliers. So the dual problem tries to locate this formula that is related to the support vectors. By support vectors, we mean the data points that are close to the hyperplane. So that can be used to solve this SVM. So the dual formulation enables the use of kernel tricks and more effective computing. So now that we've known those terms, let us see how support vector machine works. But before we go on, maybe if you have a question. Pardon? No, no, no. We cannot tackle ensemble models if we are not yet done with the single models. And so I said ensemble model is actually a combination of two or more models, or using the same model twice, so that it appears as if there are two models. So sometimes you might want to use support vector machine and decision tree in the same problem for classification tasks. So that is the ensemble model. So there was no way you could learn ensemble if you're not yet. And that's why I stopped at the point when I wanted to introduce it yesterday. Okay. So let's now see how this support vector machine works. Number one, support vector machines can actually be used for both classification and regression problem. But most of the time, I think that's a repetition and it's direct. So if, for example, you have data that has two or more labeled classes, you can use a support vector machine as a discriminative classifier and can define a decision boundary, sometimes called an optimal hyperplane, that provides a function which separates the classes. When any new data points are then mapped into the same space, and this is how machine learning works, you train it in an existing data to use it in an incoming new data or unseen data. Right now, if you implement a machine learning model for market share, we are using it for new customers, not for the already existing ones. So when any new data points are then mapped onto the same space of the others, they will be categorized into the correct class or be on the correct side of the line or plane that is the function. A support vector machine is an example of what's called a constrained optimization problem. It optimizes the space of the margin between classes. Optimizes the space of the margin. That basically means, as we say, we are always trying to maximize the margin, but also seeks to constrain the extent of this margin in relation to data points. What did we say? You can enlarge the margin as big to be as big as you may want it to be, but remember something is waiting for you, overfitting or underfitting. So it also seeks to constrain the extent of this margin. It should try to regulate the extent of the margin. So this is the visual presentation of our support vectors. As you can see, we have a small margin, but it is separating the green. Is that green or what? Light green or something? And blue, the green circles, ovals, and blue rectangles. In the other diagram, we have a very big margin, large margin, and that is now the best model. And as you can see, the support vectors have also been clearly shown. So that is the visual presentation of of support vectors. So continuing on how it works, the main objective is to separate the given data set in the best possible way, and also select a hyperplane with the maximum possible margin between support vectors in the given data set. SVM searches for the maximum marginal hyperplane in the following steps. Number one, generate hyperplanes which segregates the clusters in the best way. It doesn't have to be perfect in the first trial, but at least make sure it does it in the best way. So left-hand side figure showing three hyperplanes, black, blue, and orange. Here, the blue, that is, I think, is the next diagram. So as you can see, blue, black, and orange. So you might want to identify which one is the best hyperplane, but at the end of the day, you've tried identifying the hyperplane. Of course, you can see that the black one is the best hyperplane, but you've tried. You've not just left it at that point. So that is step one. Step two, select the right hyperplane with the maximum segregation from the either nearest data points as shown in the right hand side. So in step two, we actually select the hyperplane that separates the data points the way we wanted them to be done. So the black one takes the day. But sometimes we might have nonlinear. This one was linear and this was very easy, okay? But sometimes we might have nonlinear and inseparable planes. In some instances, as it is in the most cases, that is, it is in the most cases also in data science, uh, there are various problems which cannot be solved using a linear hyperplane. In that case, we use a kernel trick, and see the definition up there, or a kernel function to transform the input space to higher dimensional space as shown in the right. That is, the kernel trick is used to increase uh, uh, the space through which we are going to classify items. So, which means at the end of the day, we may end up not using a linear line, a linear hyperplane. So think of the z-axis as x squared plus y squared. That is basically a quadratic equation. This is just one of the transformation we are talking of. Others include linear transformation and exponentiation. So if we move to that, we can have this one here. So look at that. It means that the data points cannot be separated using a linear, or cannot be separated using a set line. At the end of the day, we cannot use kernel is equals to linear in this. So we might look for another thing. So the one that can use is something like a circle, which actually tends to separate the two into distinct classes. So the mathematical approach for transformation using the kernel function. So a linear kernel can be used as a normal dot product. Dot product any two given observations. The product between two vectors is the sum of the multiplication of each pair of the values. Do you remember the dot product? Yeah, so the linear kernel uses the dot product. So that is to say, when you have x1 and x2, it is basically x1 times x2 plus x11 times x12 x21. Yeah, acha turudi kwa diagram. Kwa nini? x10 times this again plus this times that plus this times that until you find the linear kernel that we're talking of. That is what is known as linear kernel. But the polynomial kernel is the one that I was talking about. The polynomial kernel is a more generalized form of the linear kernel. The polynomial kernel can distinguish curved or nonlinear input space. So in this case, we have 1 plus xi xj raised to d, or raised to n, where d is some known figure, degree of polynomial. The degree of polynomial is to what extent are you multiplying. It is dependent on on the depth of your data point or the size. So the degree of polynomial is the maximum number that you're going to have the power raised to. For example, if we say, let's say 1 plus x plus x squared plus x cubed plus x4. This is called 4-degree polynomial. So if we move up to plus xk or xd, in our case, we call it d-degree polynomial. The radial based function kernel, it has its own function. The radial basis function kernel is a popular kernel formulation commonly used in support vector machine classification. RBF can map an input space in an infinite dimensional space. So the formula is there. E raised to negative gamma plus xi minus xj squared. Just times, no times. Where gamma is equals to 1 all over 2 sigma squared, which can be calculated given data. I don't know. Are these formulas getting into your mind? But again, we're not going to code these formulas. We're just going to use. The only thing that should happen is that you should know when to use radial based, function based, but you have the notes you will refer, and when to use polynomial. If you feel like the data is not like the data set that we are using currently, the one for Chan analysis, it's not linear. So that data we can use radial based function kernel to classify. So at the end of the day, epsilon is a constant, negative gamma has been given. You can just calculate sigma squared. Then xi minus xji is basically to say x1 like x at the first row, the first independent variable, minus x at the second independent variable. SVM consists of initiating some unknowns and blending them with Lagrange multiplier to arrive at a decision below, as a decision rule. Oh, I didn't attach that. Okay, it was a long formula there. Nitaitafuta then nipige picha nitume, but nilipata YouTube pia, but it's a very long formula. I mean, just the mathematical behind it, how we are going to arrive at hyperplane and everything. Thank God these things have been pre-coded by those guys who developed this SVM, so our work is just to reuse them. I guess it was his PhD project, if I can remember. And lots of models are coming up. We are not saying that these are the models that, hey, watch and to search AI kusho new AI models in the last 2 years. No, I don't want the Gemini. So as you can see, this one, the Gemini wako na Gemini AI model. Then they also have another one called okay, it was gotten from the word lyrics. So Lyria, our latest music generation model. Then there is also Imagen, of course, this is for image, text to image model, yet engineered for creativity. But acha tu nini, let's see Gemini. Yes, yes. Okay, so you say, can you please name latest models that have been developed, like the support vector machine was. I don't know if that's correct English or grammar. The latest are the following. Deep learning models, ensemble learning models, the random forests, the gradient boosting machines, the ADA boost, the stacking. The other ones are generalized additive models, GAMS, kernel ridge regression, this one. So these are the models that keep on coming and people are developing them. It's just that there are so many of them outside there. It's just that they have not gotten the media attention that they should. But there are some companies which even develop their own models. They do not want to use. I mean, they do not want to make good use of the already existing ones. So it's ensemble learning. So ensemble learning is the process. Okay, do you have a question on support vector machine? Okay. So the key term is just to know the key terms there, the hyperplane, the angelos, then the kernel functions. So actually, the hyperparameter that we're going to use more is the kernel, followed by the C. So you should, the C is basically, I think C inakwanga tu ka value, but the kernel you must identify, are you using RBF, are you using linear or polynomial, and of course you've seen the functions. Now ensemble learning, the one you're asking about or inquiring about. So ensemble learning is a process by which multiple models, such as classifiers or experts, are strategically generated and combined to solve a particular computational intelligence problem. Ensemble learning is primarily used to improve the performance of a model or to reduce the likelihood of an overfitting issue. Yep. So it combines multiple algorithms to obtain better predictive performance than the one from a single model. So it involves building multiple models and then aggregating the outputs to make a final prediction. There is no predefined number of models to consider, and some business goals may require more models than others. The goal is for them not to make the same errors for the same reasons. So levels of ensemble learning. Oh, so the definition, from the clear definition, I hope you've understood what that basically. How many should I use? That's that's the business case. The business is the one to decide based on the business problem. And I said in machine learning, there's something called monitoring. Deploy, monitor, and just sit back, relax, and enjoy and wait for what next. If it doesn't work, pull it out, implement another one, monitor. If it works, yeah, get your salary increase or job promotion. So levels of ensemble learning: base learners, meta learners. So the base learn in ensemble learning kuna kwanga na the ones that actually you say this is the bazenga of this class. You know, when you are in high school, I guess Shaq was one of them in high school. When he was missing in a class, the teacher will be like, "The class is so boring today." So those guys who are, we can refer to them as base learners as far as ensemble learning is concerned. So then there are the meta learners. These are the others. Wao wako tu bora tumefanya KCSE tukajulikana, shule ilikuwa na watu 71 walifanya KCSE. Okay, now the base learners, these are the first level of an ensemble learning technique architecture, and each one of them is trained to make individual predictions. So therefore, they are the individual models or algorithms upon which the ensemble is built. So before you start building and like assembling, before you start assembling all the models, they are those ones that you can use as your decision-making cohort. So when you use them as your decision-making cohort, they are called base learners, and they are actually the ones that make individual predictions first before you introduce others. For example, let's say I want to implement ensemble learning of support vector machine and naive-Bayes classifier. I can decide that let naive-Bayes classifier be my base learner, then ensemble nini itakuja baadaye ensemble sasa support vector machine. So base learners are trained on subsets of the training data or with different algorithms to introduce diversity into the ensemble, which helps improve generalization performance. So what can you notice there? That we train base learners on subsets of the training data. We do not implement it on the full data. Or with a different algorithm, with different algorithms introduce diversity into the ensemble. So base learners can vary depending on the specific ensemble method being used. For example, in bagging, which you are going to see hapo mbeleni, bootstrap aggregating, base learners are typically high variance models such as decision trees. Then in boosting, base learners are typically weak learners, which are models that perform slightly better than random guessing. Do not worry about the new terms, you will see what they are. Meta learners, these are the second level of an ensemble learning architecture, and they're trained on the output of the base learners. So based on the accuracy score of the base learner, you can now implement a new model, and this is called meta learner. Therefore, they are the models that take the outputs of, or predictions of base learners as input. Even if it is wrong, take it as input and learn how to combine or manipulate them to make final predictions. Unlike base learners, which are directly learned from the input data, meta learners learn from the outputs of the base learners. So meta learners are often used in ensemble methods such as stacking or stack generation. We are going to see what they are at. Generalization. In stacking, base learners generate predictions on the training data, and these predictions are then used as features to train a meta learner. So it means the output, the prediction output. Hata kama they are wrong, even if they're not accurate, just use them. Then the meta learner learns to combine the predictions of the base learners to make the final prediction. So the purpose of meta learner is to capture high-level patterns or relationships in the prediction of the base learners. You see that wrong pattern that has been produced by base learner. So meta learner is trying to correct it. That is. So at the end of the day, meta learner is an optimizer of the base learner. So by learning how to combine the outputs of multiple models, meta learners can often achieve better generalization performance than any individual base learner alone. And that's why Ensemble can be a better choice compared to a single model. But again, deploy, monitor before you make decision. In fact, in some companies, what they do, uh, in big companies like Amazon, they have a pseudo Amazon, a small Amazon, which they deploy that machine learning model. Then they monitor. They form so many accounts, very, very many, even a million of them. Then they make random purchases based on the correct history. Kisha they monitor. Wakiona inafanya kazi, ndio wanaweka kwa the real Amazon. And that's why it works best for them. Market share tuko na hiyo capacity. So types of ensemble learning methods: bagging, boosting, stacking, blending, voting, cascading. Jamani, tumefika wapi huko? Bagging. The word bagging comes from bootstrap aggregating. You know what the meaning of aggregating is. But now let's look at bootstrapping. Bootstrapping is basically sampling. So from statistics, bootstrapping refers to sampling with replacement. You sample, then you replace. Two white balls are drawn from a basket, then replaced. Each base learner samples from the data with replacement. For bagging, this means that various base learners this means the various base learners all sample the sample observation, and a single learner can sample that observation multiple times during training. The aggregation part of bagging refers to the fact that the predictions of all the individual models are aggregated to produce a final prediction. This is what happened. Remember, by the way, base learners cannot just be one model. Hey, I think that is one thing I can also emphasize on. And so number one, base learner can be two or more models, and they are done on sampling. Or number two, it can be a single model, but done with sampling. You do and redo again so that you get different results. When you get these different results, you aggregate them. Then that is going to give us the final prediction. Let's say the first prediction ilisema that it will be in the class of 1. The second one ikasema in 0. The third in 1. The fourth 0. The fifth 1. Hivyo hivyo. So you will aggregate them and see which one and find the average, then round down. That is where we base our argument. So. Again, that is what is known as bagging. You do bootstrap aggregation. You implement base learning with sampling. Then after that, you aggregate the results. That is bagging. I think nishaeleza. So the bugging technique involves creating multiple subsets of the original training data. So we have different multiple subsets. If the data was 80%, you put subsets of this 80%. And then implement, if it was a single base learner, implement the base learner into all these samples. Or if there were more than two base learners, implement one in the other, or you can do with replacement, do and redo again. Again, assembly technique where data points are randomly selected with replacement. So the bugging technique involves creating multiple subsets of the original data through bootstrapping. So you take samples using bootstrapping where you can take samples with replacement. You may replace later. Each subset, also known as a bootstrap sample, is used to train a base learner independently. This is what I want to focus on. Typically, these base learners are of the same type, such as decision trees. So it is very rare to find base learners of different types, but we are not ruling the possibility. We are just saying typically. So once all base learners are trained, bugging combines their predictions through averaging for regression tasks or voting, which are going to see later, for classification tasks to make the final prediction. And by the way, near voting to year 2027. We can't wait. Very fast in the morning, I will not even look at who am I voting in as president, but I will focus on who I'm voting out as president. It's that when my heart is always bleeding that this guy, when he got into the office, we had IOPS. But I don't want to lie. I didn't vote for him. I didn't vote for him. But when he was announced the president, I was very happy and positive. So I was like, he's going to, because the Azla narrative resonated well with us. So today ndio kwa group ya hiyo meeting nimeenda, ndio mama mwingine anatuambia, so this guy kumbe alikuwa anasema we will be hustling nation, you will hustle. So the negative the negative he meant, yeah, he meant the negative part of hustling now. Then she also said, okay, it was a laughing matter, but she was right. That when Ruto got into the office, it said something. His sword menipea si ya kukata mboga. But then we had forgotten of that thing. He said it. So now, right now, you see the sword is not used to cut. By the way, the lady was advising us not to go to this. So that's where the issue of Ruto came in. So this sword is not for cutting mboga. So sasa hii ni ya kukata wananchi wenye hawana tia. Then he also said something that Kenya kuna mama matatu. The third one, you remember, atakupeleka kwa baba. Isn't he doing it? So sometimes he was saying it's a joke, but now it is making sense. Mm. But ametuchekesha sana. When people told you you guys will hustle, you thought it was a joke. Now you are hustling. Yeah. Okay, now let's go back to what we were talking about, the voting. When it is regression, we are going to find the average. But when it is classification, we vote. By voting, we look at the class that had the highest number of occurrences after implementing base learners. Huyo ndio tunaenda nayo. For example, kama ilikuwa, remember we've done on different samples. Number one, our prediction, this one was to go in the first class, the one class. The second one, zero class. The third one, one, zero, one. So tunaziangalia, tunasema one imepata 3 votes, zero imepata 2 votes. So we pick one. Yeah, but to me, if it feels more effective, because at the end of the day, uh, ili ile one ipate mingi na manisha the model was working towards one. So by combining the predictions of multiple models trained on different subsets of the data, bugging reduces variance and helps to mitigate overfitting, resulting in more robust and accurate predictions. In summary, bugging is an ensemble learning technique that improves the performance of machine learning models by training multiple base learners on bootstrap subsets of the training data and combining their predictions to make more accurate and stable prediction. I think the summary is a very good explainer. Shak, one day utaenda kwa interview ya machine learning ulizwe A company has implemented it. And the guy who asked that, a very funny guy, is like someone who doesn't know what he's asking. Then he looks sluggish in the panel. So you call yourself, anajifanya hajajua jina. You call yourself Shakil Mburu. Okay. Mr. Shah, kindly tell us. Let's assume we have developed this model and we want to improve it. What do you think we can do? What can we do? You are start scratching your head there. Oh, sikufunzwa. I did teach. It is ensemble learning. You just start to. I think we not to think. Be sure. In this case, we can implement an ensemble learning technique such as bagging, where we can actually train different base learners on bootstrap samples, then combine all their predictions to make a final and stable prediction. If it was short and clear like that, the sluggish guy will be like, I think this is the best candidate we need for the task. But it depends. Why use bagging? That's where I was coming. When to use bagging and when to use cascading. So here in a depend with the question of the interviewer. So when you want to reduce variance, standalone models can result in high variance. That is the deviation of the deviation from the predicted and the norm and the actual value. So aggregating these models prediction in an ensemble help reduce it. So that at the end of the day, if you find the average, you tend to do away with this. Unajua, when you implement these models, inamaanisha some will be lower, others will be higher. So when you average them, you've taken into consideration both the lower, the mid, the moderate, and the high class. So what if you just used one and you got a higher value? So basically, I love the word you've used, bias, which is variance. It basically means that the variance will be so big. But now that you've used averaging, we've reduced the variance. Fast training can happen in parallel across CPU cores and even across different servers. Good for big data. Bagging doesn't require an entire training dataset to be stored in memory during model training. You can set the sample size for each bootstrap to a fraction of the overall data. Train a base learner and string these base learners together without ever reading the entire dataset all at once. But the individual models, we do it on all the training data at once, which eats up on our memory. Graphical representation of bagging. Original training data, unaona tuko na sample 1, sample 2, sample 3, sample 4, or sample n. N different samples of original data. Then you implement decision tree, then there is also a real tree. You implement a decision tree 1 on the sample 1, decision tree on sample 2, then you aggregate. My work is finished with the explanation at that point. Yeah, is there anything we need to explain on that? Yeah, labda if it is not shark. Then we have the advantages of bagging. I think the process is straightforward and does not require any deep mathematical concepts. So the only thing you need in mathematical concept part of it is when you start from the individual base learner. For example, the decision tree. You first must have to know how decision tree works is when you implement it in bagging. The scikit-learn package makes it easy to implement the underlying logic. It contains all the modules to combine the prediction of each model known as base learners. So it has a significant effect on reducing variance on high variance classifiers. We've explained that. And also produces an unbiased estimate because the averaging has been taken care of. Everything that has an advantage. Number one actually is very straightforward. Expensive due to use of several models. Base learner 1. Si unaona kitu tunafanya hapa. Decision tree 1 on sample 1. Decision tree 2 on sample 2. So those are so many models and they eat on our memory. Even though the data is trained on individual data set, but at the end of the day, it is expensive. Number 2, the average involved across prediction make it difficult to interpret the final result. Haujui if it is the real result because you just averaged. But the first one gave the real data. The second one gave another one, a different data. But when you now find the average, where should we base the argument on? At the end of the day, it's just an average, so it's very difficult. And the one type of bugging algorithm is random forest. So in short, Shark, the graphical representation here just represented random forest. So I'm done. So in that case, random forest has been implemented. I think we can stop at that point. Too much theory is not good for the brain, especially in data science. Have you ever realized that you can code for 2 to 5 hours, but, yeah, but you can never read the theory for 2 to 5 hours? So I wanted us to finish up to random forest or bugging. Sasa bugging classifier, uende usome hiyo module. I think I tried my level best nikaweka hadi. I was a very good data science teacher, putting even the links. Sometimes I go through these notes and I'm like, where did I get all this time? I was so lazy. Then okay, but it happened that I got this job and nilifika kama the student walikuwa wamefanya the data analyst part of it, so alikuwa anabaki na machine learning. So they wanted a machine learning engineer. I think they got one. Si kujiringa, but uh, I was so deep into it. This is like I'm now going to work as a machine learning. I was working, but not. I just as a data scientist, as a BI developer, something sort of. So I've gotten the machine learning job I wanted. Why can't I be serious in it? Only to realize that all is vanity.